Hey guys, welcome back. So in this video, we're going to do an AC analysis of a common base transistor amplifier. So here we have our, so notice this is not an NPN transistor, it's a PNP transistor. All right, so this is a PNP transistor. So hence the arrow pointing towards the base. So this is a PNP transistor. So it's arranged in a what we call a common base configuration, where the base is the common for both input and output. All right. So as usual, whenever we want to do an AC analysis, we need to convert our circuit into an AC equivalent circuit. Now, for a common base transistor, the model that we're going to use is still an RE model, but the RE model is a little bit different from the one we typically use for common emitter and common collector. So in this case, we have just an RE instead of a beta RE between the emitter and base, between emitter and base, emitter and base. And then we have a dependent current source that represents IC. The IC, the current is coming out of the collector there. And is given by alpha IE. So IE is the emitter current that is flowing in. Okay, IC is the collector current is flowing out. Okay, and we can also have an RO. Okay, we can also have an RO. Again, RO is typically very large, so if you're connecting anything parallel to RO, the RO becomes insignificant. It is large enough because it's a parallel connection, right? So as usual, in order to do AC analysis, like I said, you need to do the three common steps in that transformation. The first of all is that you need to short any capacitors that you may have in the circuit. Well, in this case, there aren't any capacitors. Okay, so there aren't any capacitors, so that's done. Next is to zero all DC sources. Well, there are two DC sources here. One is VEE, the other one is VCC. So you have to turn that into 0 volts, which means this becomes a, well, it doesn't exist anymore. Once it becomes 0 volts, this is effectively just a piece of wire here and a piece of wire here. So these two DC sources will become 0 volts. And then finally, you replace the transistor with the RE model for a common base transistor. So once you do all that, this circuit is fairly straightforward. So you're going to get a circuit that looks like this, an AC analysis circuit that looks like this, where you have in the middle there the RE model replacing the original transistor. So RE at the bottom of RE becomes just a wire, because obviously VE becomes 0. And similarly for RC, the bottom of RC just simply connects to the bottom, to the base, right? This is the base, because VCC becomes 0. All right, and so let's analyze the circuit as per usual. So, well, we're required to, as usual, discover what is ZI, ZO, AV, and AI. So let's start with ZI. All right, so let's start with ZI. So let's have a look at ZI. Okay, all right. So I'm going to write ZI over here. So if you look at ZI is the input impedance as seen by VI. So it's looking towards, from left to right. Straight away you'll notice that all the ZI is going to see are two resistors in parallel. So I think ZI is fairly straightforward. All right. So ZI is going to be equal to RE parallel with little RE. All right. And that's it. That is ZI. So fairly straightforward. Now ZO, if you look at ZO, it is the output impedance as seen by VO, looking from right to left. And as usual, whenever we want to work out what the output impedance is, we need to zero the input voltage. So to discover ZO, we must zero VI. All right, so that's the procedure for figuring out what ZO is. So therefore, you're going to get okay, and then so when you do that, well, when you zero VI, what's going to happen? Well, the top node and the bottom node will be connected because this is 0 volts. So that means the top and bottom will be connected, which means the nodes at the top and the node at the bottom will have the same potential, which means there is no more IE, right? Because there's a 0 volt difference. There's a 0 volt potential difference across RE. So therefore, IE is going to be 0. So if IE is 0, then alpha IE is also 0. So that means the only thing that ZO will see is just RC. Now, by the way, in the model that I showed earlier, it has a little RO. So a little RO would have appeared here, right? The little RO would have appeared here. So if the little RO is there, then ZO would have been the parallel of RC and little RO. All right. So in this case, because we're assuming RO is very large compared to RC, that means at least 10 times bigger. So therefore, we just can take out RO. All right. Leaving just RC. So to discover ZO, we must zero VI. So therefore, ZO, all right, is simply going to become RC, all right? Okay. So therefore, ZO becomes RC. So we're done. So that's pretty much it about ZO. So this is fairly easy to figure out what ZI and ZOs are. The impedances are, right? Input and output. All right. So next we'll work out what AV might be and what AI might be. So now for AV, voltage gain, right? So the voltage gain, AV, right? AV. Well, is going to be you can do like, for example, AV is what? AV is obviously just V out of V in, right? So that's basically the first thing that you probably have to write. You should write so that you're clear as to what it means. All right. So the problem now is to try and find out an expression for VO. All right. Okay. So expression for VO means the voltage across, in this case, across RC. Well, IO is defined as going up. So to figure out what VO is, right? So figure out what VO is, then obviously you need to reverse IO. Yeah, because VO is pointing up and IO is also pointing up. So if you want a positive VO, then we need a negative IO. That means an IO current that is flowing the other way, that is coming down. All right. So we can represent VO, all right, VO, using, again, Ohm's law, V equals IR. So IR here is basically negative IO times ZO. ZO is basically the impedance seen by VO, right? So therefore, at the top part is going to be negative IO, right, times ZO. All right. So that is going to be our VO divided by, so let me just put this in brackets, divided by VI. Well, what is VI? Well, VI, similarly, it's just going to be II times ZI, right? II times ZI. So it's fairly straightforward. So II times ZI. All right. So that's what VO over VI is going to be. Okay. So we still need to figure out what IO is. We still need to figure out what II is because, well, ZO and ZI we already have. So we just need to figure out what IO and IIs are. So let me just before this voltage gain part, let's just figure out an expression for IO and II. So, well, what is IO? If you look at IO, well, it's actually the negative of alpha IE, right? Or is the negative of IC. So alpha IE is flowing this way in a clockwise direction. So, well, since there's no other load here, so all of that is just going to flow through RC in the opposite direction of IO, right? So therefore, I can write here, IO is going to be equal to negative alpha IE, right? So that's basically what IO is. Okay, so very simple. So in the case of II, in the case of II, well, what can I write? Well, actually, you can write in terms of a relationship between II and IE, because IE is obviously a current divider, right? So, you know, II splits between that flowing through capital RE and IE that is flowing through little re. So that's what II is going to do. It's going to split between these two resistors. So we can write an expression for IE relating IE, RE, small re, big re, and II in terms of a current divider rule. All right. So I can write here using current divider rule. All right. So my expression for IE is going to be equal to II, which is the total current that is flowing into the branch, all right, multiplied by capital RE, all right. So this is just basically current divider rule, all right. All right, so that's what it's going to be. All right, so IE rather is going to be that. So now we can write it in terms of II. All right, so that means I just basically move everything from the right side to the left side. So then I'll get an expression for II, which I can then use in the original expression for working out AV. All right, so I can say here, therefore, II is going to be equal to IE multiplied by at the top will be R underscore E, sorry, RE plus little re divided by capital RE. All right, and that's it. That's basically what II is. Okay, what I want to do next is I want to simplify ZI and II a little bit more, based on the fact that little re is typically much smaller than big re, right? So let's have a look at ZI first. So I'll say typically little re is much smaller than big re, all right? So I can say therefore I can simplify ZI a little bit more. Well, first I'm going to expand RE parallel, big RE parallel with little re. So that's basically this times this, all divided by this plus this, right? That's your typical parallel resistance equation, two resistance equations. So if RE is very much smaller than big RE, then the little re at the bottom there is going to be insignificant compared to the big re, right? So, you know, a big number, that's capital RE, plus a very small number, come on, I wanted to highlight this, all right, would make that particular expression at the bottom to be just capital RE, right? So this is going to be approximately equals to you know, capital RE at the top there is still capital RE divided by RE. All right, so it's approximately equal to that, and of course, big RE will cancel out top and bottom. All right, therefore leaving just a little RE as the final outcome. All right. All right, so that's basically the much simplified version of ZI. It's just going to be a little RE. And similarly here, again, if I say typically little re is much smaller than big re. Yeah, remember, yeah, when I say much smaller, it needs to be at least 10 times smaller. to make this approximation more accurate. All right. So typically RE. So then I can say even for II, therefore I can write an expression for, or rather I can simplify the expression for II in a similar way. It's going to be I times E. All right. Multiplied by well, little re is very small compared to big re. So okay, let me just rewrite this anyway. So let me just rewrite this to so that it's clear to everybody. All right, divided by re. Okay. So then obviously this one becomes very small. This little re is going to be insignificant compared to the big re. So that's going to disappear. So when that disappears, you just left with big RE divided by big RE. So those two will also cancel out. So meaning that you're going to have, okay, let me just write out just for complete sake. IE, oh sorry, equals to, so equals to IE times RE divided by RE, right? Okay, so these two cancel. The RE top and bottom will cancel out. Okay, so leaving just, of course, IE. Okay, done. Let me adjust this a bit so that it will fit on the line. Yeah, it's going to become okay. So if you look at the expression, it's negative IO ZO, so there's a negative in front. IO is just over here, which is negative alpha IE, so negative alpha IE times ZO. ZO is just RC, yeah, from here. So times RC. All divided by II. II is simply, there it is, IE. So all divided by IE times ZI. ZI is little re, all right? All right, so it's going to become, oh, sorry, I forgot to close the bracket. Hang on. I need to close the bracket over here. Wait. I think I'm going to close my bracket. Not over here, but over here. So that the top part and the bottom part will separate. Yes, there you go. So therefore, it's just going to be equal to, well, the minus and minus will become positive. So it's just going to be, and of course, IE will disappear, will cancel out because they exist both top and bottom. All right, so what's left is just going to be positive alpha times RC divided by little re. Okay, and then typically, since alpha is 1, so you can approximate that to be simply RC divided by RE. Okay? Okay, so that's AV. Now, the final one is AI. So, well, what is AI? AI is the current gain, and is defined as the output current divided by the input current. The input current, all right? So IO over II. All right? And we have expressions for all of them, so it's negative alpha IE, that's for IO, all that is divided by II, which is simply just IE. Right, so obviously IE will cancel out, top and bottom. Leaving just negative alpha. All right, which since is approximately 1, so it's going to be approximately negative 1. All right. So that's it. We now have expression for everything. We have an expression for Zi. We'll just highlight them. We have an expression for Zo, an expression for AB, and finally an expression for AI. Okay, thanks for watching. I'll see you guys in the next video.